What's up, AP Calc students? Mr. Ford here, recording a live homework answer guide for 5.2.5. This is probably going to be a part one since we have about 8 minutes left in this class, so we'll do the first few problems, and then I'll record whatever we don't get done now. I'll record after school, and then I'm going to go home and not think about school for a while. 5.2.5, which I suggest for the rest of you too. These are the dog days, man. I was telling Kara Grozier before this class started, we are definitely, if you're thinking about the pace of this class is really pushing, we're definitely at an inflection point right now. The roller coaster is at its steepest moment. We are going as fast as we're going to go as far as pace-wise. Things will level off, certainly, as we move into chapter 7 and 8. But always thinking about those slopes, always thinking slopes. That's what you want to be doing for success here. That is the theme of this class. Calculus is cool because it really revolves around, like a lot of math classes beyond algebra, it revolves around like one central idea. So let's jump into 104. We have a really simple function, x to the 1/3 power. We're going to use the formal definition of continuity to determine if it's continuous at x equals 0. Formal definition of continuity says the following thing. Does the limit as x approaches 0 of f of x exist? Question 1, does this limit exist? And it absolutely does. If you approach it from both sides, you get the same thing. We could graph it right now. That might be a good thing to look at too. X to the 1/3 power, just to get a look at. There are going to be no jumps in the graph or spots where it doesn't work. I'm just going to leave it right down there. It's very small on this screen for you guys in class, but it's going to be, you can blow it up if you want to. Thing number 2 would be, does f of 0 exist? And again, yes, it's equal to 0. And question 3 is asking the question, does the limit as x approaches 0 of f of x equal f of 0? And again, the answer here is yes. They are all the same thing. So since the limit exists and since the function exists and they are the same thing at that point, yes, you have a point of continuity at x equals 0. That's a little bit overkill. Now, as far as this question goes, calculate the limit as x approaches 0 of f of x minus f of 0 over x minus 0. Knowing how to read this helps out quite a bit. All you're really looking for here is the derivative at 0. If you think about it for a moment, the kind of the secondary version of the formal definition of a derivative, it says limit as x approaches c of f of x minus f of c over x minus c. In this case, we are looking for c equaling 0, and so that's the f prime of 0. Which in this case is going to be 0 also, but we'll at least take a look at the derivative. F prime in this case is 1/3 times x to the negative 2/3 power. And actually, if I'm thinking about this really quickly, it doesn't equal 0. It's actually going to be undefined, since this derivative has all that stuff happening on the bottom of the fraction. It's the cube root of x squared. If you were to plug a 0 into the bottom of that fraction, you would get an undefined thing. So this actually does not exist. The derivative at 0 is undefined. The limit in part B, of course, is just representing the derivative, f prime of 0. We kind of already talked about that right there. And what's graphically happening at x equals 0 that causes that to happen, let me walk over here and blow up calculator cam for a moment, because I think you'll see it if you look at it carefully. I'll have to zoom way in on it too. But right at x equals 0, you have what's called a vertical tangent line. You can barely see it on this graph because the window's a little wonky, but the graph goes really vertical at that point, and vertical slope can't exist. And since slope is the derivative doesn't exist at that point. So remember, your critical values happen whenever the function is, or the derivative is 0, or when it doesn't exist. So what's happening graphically is you have a vertical tangent line. The slope of that tangent line does not exist. Moving on into 105, another really powerful concept. We saw this a while ago, I want to say on the chapter, or on the semester 1 exam actually. You can use tangent line to estimate the value of a function at points near a point of tangency. We're going to sketch a quick graph of this square root of x plus 1. Again, I'm going to kind of use calculator cam to help me out with this one. Square root of x plus 1. It's just going to be a square root of x graph that's been moved one spot to the right. So the graph kind of looks like this. There's negative 1 right there. It goes like this. Right there. And we're looking specifically for its tangent line at x equals 0. So again, tangent lines being a really central concept to this class and to derivatives in general, there's kind of the tangent line at x equals 0. Just a quick sketch of what's going on here. The other thing we got to do is to write the equation of that tangent line. That's actually going to be pretty easy to do in this case. We kind of know that that point right there has to be the point 0, 1. And for its slope, we can just use the derivative. We have the original function f of x is equal to the square root of x plus 1. And its derivative, f prime of x, is 1 over 2 times the square root of x plus 1. And in this case, we really want to know what f prime of 0 is. That's going to be 1 over 2 times the square root of 1, or 1/2. So using the point of 0, 1 along with the slope of 1/2, you can easily write the equation of this line. It would be y minus 1 equals the slope of 1/2 times x minus 0. Or more simply, y1 is equal to 1/2 x. Or even more simply, y equals 1/2 x plus 1. That's the equation for that tangent line right there. A lot of Algebra 1 stuff happening here, a lot of point-slope form, a lot of quick ideas coming back to us. Question B tells us to use the tangent line to approximate the value of this function for x equals 0.1 and x equals negative 0.1. We can actually do this really easily without a calculator, because all we're going to do here is we're going to plug into this function. We're going to evaluate 1/2 x plus 1. We're going to do this when x is equal to 0.1, and we're also going to evaluate it when x is equal to negative 0.1. Which is actually relatively simple to do. Actually, it might be better, the more I think about it. It's fine. 1/2 times 0.1 plus 1, and y equals 1/2 times negative 0.1 plus 1. Let's see. 0.5 times 0.1 is going to be 0.05 plus 1, and this is going to be negative 0.05 plus 1. So you're going to get 1.05 and negative 0.95 for these two answers there. Just plugging in 0.1 and working through the function that you built back in part A. Now, the calculator is going to actually come along and actually evaluate what the square root of 1.1 and the square root of 0.9 is. Thanks for being here, guys. I'm going to finish this problem, and then I'll stop. All we got to do here is, well, what we're doing here is comparing what the actual value of the square root of x plus 1 is compared to these estimations that we got back over here in these parts. This is for part C. The square root of 1.1 and the square root of 0.9. What we're doing here is we're comparing the actual value, the square root of 1.1, which is equal to 1.04888, and the square root of 0.9, which is equal to 0.9487. So we're getting about the same answers. There's a little bit of error between these two answers, but this is an estimate based on a projection that we built back in part A. This is the actual answer that we get from our calculator. The whole idea is that the estimate is able to do without a calculator and pretty quick, and the actual requires this technology. So there's a bit of difference on what you can do there. I'm going to go ahead and put the pause on this video right now. I'm going to record part 2 after school today, but we'll jump into 106 in the next video. Don't forget, you guys are awesome, and I'll see you next time.